Data centers represent a fundamental transformation in how electricity is consumed in the modern digital economy. These centralized physical facilities house the computing, storage, and networking infrastructure required to process, store, and transmit vast volumes of digital data. From a power system perspective, modern data centers, particularly hyperscale, cloud, and AI-focused facilities, are no longer conventional commercial loads. Instead, they function as large, concentrated, high-density, and highly dynamic electrical loads, often comparable in magnitude to industrial plants or small cities. The evolution of data center power requirements has been dramatic. Traditional data centers typically operated at 5 to 10 kilowatts per rack, while modern hyperscale facilities demand 20 to 50 megawatts per data center. The emergence of AI-optimized facilities has pushed power density even further, requiring 60 plus kW per rack within the same physical footprint. According to industry projections, AI-related power consumption could represent 50% of total data center energy by 2025. This growth is reflected in overall electricity consumption. Data centers accounted for 4% of total U.S. electricity use in 2024, with demand expected to more than double by 2030. As digitalization, artificial intelligence, and cloud computing accelerate, data centers are becoming critical nodes within the electric power system, directly influencing system operation, planning, and stability at both transmission and distribution levels. This transformation requires a fundamental rethinking of how utilities and system operators approach load management, infrastructure planning, and grid operations. The traditional model of treating data centers as passive consumers of electricity is no longer adequate for addressing the challenges and opportunities they present to the power system. The impact of data centers on power system operation is multifaceted and significant. Perhaps the most immediate challenge is their massive and concentrated power demand. Data centers exhibit extreme load concentration within limited geographic areas, with individual hyperscale facilities routinely demanding 50 to 100 megawatts or more, and campus-style developments exceeding several hundred megawatts. This concentration significantly alters local load flow patterns, stressing substations, feeders, transformers, and transmission corridors. Distribution networks originally designed for diversified, low-density loads may experience thermal overloads and voltage regulation challenges. At the transmission level, large data centers can influence regional power balance, forcing redispatch of generation and congestion management actions. Unlike traditional industrial loads, modern data centers, especially those supporting AI and machine learning workloads, exhibit rapid and stochastic power variations. GPU clusters and high-performance computing systems can ramp power consumption up or down within seconds, introducing challenges in frequency stability. Sudden load increases cause frequency dips, while abrupt load shedding can create overfrequency conditions. Conventional governor and AGC responses may be too slow to counteract these fast load flapping events. Similarly, large step changes in demand can lead to voltage sags, flicker, and increased reactive power requirements, threatening voltage stability. Data centers also affect power quality through their reliance on power electronic interfaces, including switch-mode power supplies, uninterruptible power supplies, UPS, variable speed cooling drives, and rectifiers for DC bus architectures. These devices introduce harmonic distortion, degrading voltage waveform quality, and create low power factor, increasing reactive power demand. From a system operation perspective, poor power quality can increase system losses, cause misoperation of protection devices, and accelerate aging of transformers and capacitors. The stress on aging grid infrastructure represents another significant challenge. Much of today's grid infrastructure was designed decades ago for predictable, slowly varying loads, unidirectional power flows, and limited power electronics penetration. Data centers challenge these assumptions by introducing high, continuous thermal loading, rapid power ramps, and potential bidirectional flows when on-site generation or storage is deployed. Grid reinforcement, new substations, transformers, and transmission lines typically requires 3 to 10 years, while data centers can be built and energized in 12 to 24 months, creating a significant planning-execution mismatch for system operators. The environmental and economic implications are equally substantial. To maintain reliability under high data center demand, utilities may need to commit additional fossil fuel peaking units, delay retirement of legacy thermal plants, and increase reserve margins. This can conflict with decarbonization targets, increase system operating costs, and shift grid upgrade costs to ratepayers. For example, utilities assigned $4.3 billion in connection costs for data center projects to customers in 2024 across 7 mid-Atlantic states. Wholesale electricity costs have increased as much as 267% over the past 5 years in areas near data centers, highlighting how data centers have become a system-level policy, economic, and environmental issue, not merely a technical one. While data centers present significant challenges to power system operation, they also offer unique opportunities as active grid participants. Modern data centers possess substantial on-site assets, including UPS battery systems, standby generators, and power electronics with fast response capability. These resources can provide valuable grid services, transforming data centers from passive consumers into flexible grid resources. Data centers can contribute to frequency stability through fast frequency response, FFR, providing quick response to frequency deviations that conventional generators may be too slow to address. They can also participate in demand response programs, reducing consumption during peak periods or grid stress. Through their power electronics, data centers can provide synthetic inertia, emulating the inertial response of traditional generators, and offer voltage support by providing reactive power to maintain voltage stability. By temporarily reducing load or islanding from the grid during contingencies, data centers can actively contribute to system stability. Flexible interconnection models are emerging as a key enabler for this transformation. These models, often referred to as Bring Your Own Capacity, BYOC, can reduce data center burden on the grid while accelerating deployment. In a BYOC model, part of the load is supported by a firm service agreement and the remainder, about 20%, with conditional or interruptible service. When grid capacity is constrained, the utility can interrupt service on the conditional portion, requiring the data center to reduce its load or use on-site resources to make up the shortfall. Despite these flexibility requirements, data centers would still be able to use grid power more than 99% of the time, with curtailments needed only 40 to 70 hours per year. Several companies are pioneering this approach. Google is implementing AI-powered flexibility to speed data center connection, with analysis showing that curtailing just 0.25% of annual data center energy use during peak hours could free up 76 gigawatts of load, equivalent to powering 50 million homes. A collaboration between NVIDIA, Emerald AI, EPRI, Digital Reality, and PJM aims to build the first power-flexible AI factory, which Emerald AI claims could unlock 100 gigawatts of capacity on the existing electricity system if adopted nationwide. This transformation from grid liabilities to grid resources represents a paradigm shift in how we think about the relationship between digital infrastructure and the power grid. It requires a shift in mindset from both utilities and data center operators, as well as the development of new technologies, business models, and regulatory frameworks. With the right approach, data centers can evolve from being one of the biggest challenges facing the power system to becoming one of its most valuable assets for maintaining reliability and stability in an increasingly complex energy landscape.